Hey, welcome to class. This is Math 120 Fundamentals of College Mathematics. This chapter is set theory. We're going to talk about, let me get this slide going here, basic set concepts, and here's our objectives. We'll start out with talking about the ways to represent sets initially. So first of all, a set's a collection of objects. As it says here, whose contents can be clearly determined, and those members of the objects are called elements. They must be well defined. Here's a capital letter is usually used to name the sets. So here's an example for, well, let me get this. Sorry about that. So here's an example. You see the capital W right there. We use the capital letters to represent or to name the set, and this is a word description. So if we were creating a set with the days of the week, that's how we do that. And you've got commas that are used to separate the elements of the set. You've got these braces right here, right? These are called braces, um, in which the elements are enclosed within that set. So here's a word description. If you were to write a word description, I'm sorry, of this set here, you got capital P, you got Washington, Adams, Jefferson, Madison, Monroe. If you were to write a word description, you just say, oh, that's the first 5 presidents of the United States. That's set P. If you were to write using the roster method, so set C is a set of US coins with a value of less than $1, you'd say, well, capital C is the set, coins less than $1, and you'd write them out. Penny, nickel, as you keep going here, I've got a dime, quarter, $half. And that's with the roster method, right? You've got the braces outside, you've got a comma between each element of the set. Here's your elements of the set, right? Members of the set there. Now you've also got, so besides word description and the roster method, we've also got set builder notation. Um, so this is how you read this is you say set W is the set of X such that. So this vertical line right there means such that X is a day of the week. Right? Set W is a set of all elements X, again, such that X is a day of the week. So let's express this set, which is right now in set builder notation, and let's put this in the roster notation, if you will. So the set of all elements X, such that X is a month that begins with the letter M. So if we were to do this in roster method, we say, oh, that's March and May. Okay. Now the empty set. So this is also referred to as the null set. This is just simply a set with no elements in it. So you can express it this way with braces and nothing in it, or you can just write it with the empty set notation. Okay, so here's an example. Set of all elements X such that X is a fawn that speaks. Well, we know that there's no fawn that speaks. We do know there's a horse that can talk. Horse is a horse. Horse, of course. No one can talk to a horse, of course. Unless, of course, horse is the famous Mr. Ed. Okay, that's a really bad joke, but anyways, showing my age with reference to Mr. Ed, the speaking horse. But anyways, we got a set of all numbers less than 4 and greater than 2. Well, is there any numbers that are less than 4 but also greater than 10? I'm sorry, I said 2. But also greater than 10? No, none of them are. So that'd also be empty set. Both of these are just the empty set. Now, which of the following is the empty set? So let's look at this set right here. We got a set, and who's in that set? Well, it's a set, but there's an element in there, and the element's 0. So is it the empty set? No, it's not, because it's got an element in it. Is 0 an empty set? Well, first of all, it's not even a set, right? We don't even have it in the braces or anything. This is just a number. It's not a set. How about these? X such that every set of all elements X such that X is a number less than 4 or greater than 10. Well, or means it could be one or the other. So a number less than 4, or it could be a number greater than greater than 10. So you can have 3. 3 works, right? Because that's a number less than 4 or greater than 10. Again, it's one or the other. So again, this is not an empty set. If this was and, like we talked about before, that's different. Um, that'd be the empty set. All right, x such that x is a square with 3 sides. Well, is there any square with 3 sides? No. So this is definitely an empty set. This is yes. This is an empty set. There's no square with 3 sides. Empty set or with the either notation on that thing. All right, notations for set membership. So this element, this symbol, I'm sorry, means is an element of, and this one just means is not an element of the set. Okay, so for example, determine whether these are true or false. So R is R, this again is an element of, in other words, is it a member of this set? So we've got A, B, C, and notice dot, dot, dot. So it includes all those letters of the alphabet, clear up to Z, right? So is R in there? Sure, R is listed in there, so that's true. R is a member of that set. Is 7, and again, this is true. 7 is not an element of 1, 2, 3, 4, 5. So the set containing 1, 2, 3, 4, 5. Well, that's true because 7's not in this set, right? So that's a true statement as well. How about this one? The set, now notice how I say this. The set containing the element A is an element of the set containing A and B. So this is a little tricky, but this one's false. Now that would be true. This is true, right? But this is not. That's not, because you would have to have, the only way to make this true is we would have to have something like this. The set containing A is an element or is a member of the set containing A. Now that would be true. But as is, this is false. Okay. All right, the set of natural numbers. Now, a lot of the time you'll see textbooks writing the natural numbers like that. So these are just your counting numbers, right? 1, 2, 3, da, da, da. And that just means they just keeps going, goes on forever, right? It's an infinite set there. Express each of the following sets using the roster method. So set A is a set of natural numbers. Remember the natural numbers. Keep going. 1, 2, 3, counting numbers less than 5. So set A is set of natural numbers less than 5. So you'd less than. Set B is a set of natural numbers greater than or equal to 25. So we're going to include 25. Greater than or equal to. So 25, 26. Obviously, we can't list them all, so we just say dot, dot, dot. Set E is the set of all elements x such that x is an element of the natural numbers. So we have the natural numbers, and we've got it, but it's also got to be even. So if we're to list them, it's got to be a natural. So we've got all the natural numbers, right? Here's our natural numbers. And so this means intersection of. And it's got to be even. Well, here's our evens, right? 2, 4, 6, 8 keeps going. So intersection means it's got to be in both. So 2's in both. Obviously 4's in both. 6 is in both. And it keeps going. So the overall set, you just list, it's a natural number and it's even. 2, 4, 6. There we go. And means it's got to be in both, right? That's intersection. It's got to be in both. Or means one or the other. Union. All right, here's some inequality notation to remind you. X is less than A. So for example, if we've got a natural number and it's got to be less than 4, we just have 1, 2, 3. If it's less than or equal to, if it's a natural number and it's less than or equal to 4, now we got to include the 4, right? If we're a natural number, right, the counting number, and it's also got the requirement that it's got to be bigger than 4, then we'd have 5, 6, 7, 8. If it's a natural number and it's got to be greater than or equal to 4, now we're going to include the 4 and keep going. All right, how about compound inequality? So if you've got, just to remind you how you say this, here's how you say it. You say x is less than b, and then you got to say this the other way. So I flip that around. Instead of saying it that, you got to say x is greater than a. So x is less than b, and it's also greater than a, right? It's between them, right? It's between them. It's less than b, but it's also greater than a. Less than b, greater than a. So for example, you've got the natural numbers, and it's also got the requirement that it's got to be between 4 and 8, right? So 5, 6, 7. How about this one? Natural numbers, and it's less than or equal to 8, but it's also greater than or equal to 4. So now we're going to include the 4 and the 8 on that. Natural number less than 8, so we're only going to be 7, but we're greater than or equal to 4. So we include the 4, right? Those between. Natural number less than or equal to 8, so we're going to include the 8, but we've got to be greater than 4. Greater than 4, so we can start at 5. All right, express each of the sets using the roster method. So we're a natural number and we're less than, so counting number, and it's got the requirement, again, intersection, we've got to be less than or equal to 100. So we're going to start out, we're a natural number. These are definitely less than or equal to 100, but I'm not going to list them all, so I'm going to go right up until 100, and I'm going to include it because I got an or equal to on that. So 100 is my last one. Natural number, but this time we got to be less than 100 and greater than or equal to 70. We can include that 70. So 70 is going to be our first one up until we can't include 100 because I got to be less than 100. So 99 is our last one. So 70, 71, 72, 73, dot, 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 up until 99. I should have a little comma up until 99. Oops, there's the answers there. All right, cardinality. So what does cardinality mean? The cardinal number of a set, represented by that right there. And what I like to say is number of elements in set A. When I see that, I like to say number of elements in A. Number of elements or members of the set. Number of elements in A. That's what I like to say. Now you read that, you'll also hear that say N of A. N of A, the number of elements in A. Okay, so it's a cardinality. Now notice it says distinct elements in set A. Distinct elements in set A is a cardinality. So for example, if I have A, B, C, D, E, A, and this is set A, the cardinality, the number of elements in the set, 1, 2, 3, 4, 5, but I don't count that again. It's distinct elements. Is the cardinal number of a set. All right, so find the cardinal number of each of the following sets. So the number of elements in A here, say 1, 2, 3, 4. How about the number of elements in B? Well, it has just 0. 0 is the only number, so we got 1. What about 13, 14, 15, 22, 23? Let's see, 30, 40, count them on your fingers. What is that, 11? 11 there. All right, so equivalent sets. If I've got two sets that are equivalent, that means they contain the same number of elements. So notice the notation here. These are equivalent. This means equivalent. This is different than equal. Equivalent sets have the same number of elements. So for example, set of all x such that x is a value, we got A, E, I, O, U. And then over here we've got natural number And we've got the restriction that it's got to be less than or equal to 7 and greater than or equal to 3. So we've got 3, 4, 5, 6, 7. Well, notice that there's 1, 2, 3, 4, 5 in A. And notice in set B, you've got 1, 2, 3, 4, 5. So they are equivalent sets. They're not the same set, right? They're not equal sets. They're equivalent sets. Just have the number of elements. Okay. All right, let's look at this one here. We got set A is a set of 5 countries here. So we've got Zambia, Colombia, Poland, Italy, United States. So number of elements in set A is 5. Now set B is a set of the average number of years women in each of these countries prefer men who are older than themselves. And then are these sets equivalent? Okay, so we're set B, we're looking at the women here. So let's say I was listing out set B, right? We would have 4.2, 4.5, 3.3, 3.3. These are those countries, right? And if you're reading this graph, this is just saying, like in Zambia, the women on average prefer their men to be 4.2 years older. In the United States, the women prefer men that are 2.5 years older. Okay, but anyways, if I listed them all out, notice I've got the repeat here, 3.3. So how many elements are in this set? 1, 2, 3, 4, not 5. There's only 4. Are these sets equivalent? Well, obviously not, because one's got 5. There's 5 countries. There's only 4 distinct elements in set B. 5 does not. It's not equivalent to 4. So these are not equivalent, and that's all that this is saying. You can also set up a one-to-one correspondence if you want. All right, finite sets and infinite sets. So set A is a finite set if the number of elements in A is 0, in other words, the empty set, or if the number of elements is any natural number, right? Like if you've got 5 or 6 or 100 or whatever it is, it's some natural number. You've got a certain number. So it's either the empty set means it's a finite set, or there's a certain amount that you can count, right? Now, a set whose cardinality is neither of those is called an infinite set. An infinite set, right? So let's talk about equality of sets. So now this is a little different. Set A, before we talked about equivalent sets, right? Set A is equal to set B, means that set A and set B not only are equivalent, they have the same number of elements, but they also have the same exact elements. Same exact elements. That's the requirement. So it doesn't matter what the order is. So 4, 8, 9, those are exact same as 8, 9, 4. 1, 3, 5, we have 1, 3, 5, but oh, there's an extra one. These are not equal, right? These ones are, that's true. These are not equal. Again, they have to have the exact same elements to be equal elements, okay? All right, that's this section. We've covered all objectives. Talked about 3 methods to represent sets, our roster method, our word description, our set notation. We talked about the symbols element of, not an element of. We talked about natural numbers, the counting numbers, cardinality. We talked about equivalent sets, finite and infinite sets, and we also talked about equal sets. Okay, so I'll see you guys next time. Thanks for listening and taking notes.